I want to show you one of my early slideshows. This one is older than you are, probably 20 years old, and this was one of my first CGIs for the classroom, and it was such a head turner at the time. Now it would be dead easy to make, but I'm not giving up on this one. This took me a lot of programming to make this one happen, and you can see the graphics, how grainy they are compared to today, so quite a lot's changed. So I want to show you the relationship between the table here and the orbital diagram that you've been doing. There's an old expression, you got to get your head around it. Quite literally, you should get the table around your head. If you could take this table and wrap it around your head on a sheet of paper, you would have this structure here. One of these orbits is one row on the table. The second orbit is the second row. The third orbit is the third row. You never need to memorize the 2, 8, and 8 pattern because it's sitting here right there. 2, 8, and 8. The term orbital or shell, I tend to prefer shell since the electrons are not in orbits. If you think of them in orbits, then it kind of means that looking at it from above, we could reach in and touch our fingers on the nucleus in the same way if there's a spinning fan blade, you might carefully go in and touch the hub. The fact is the nucleus is invisible. The electrons are like a force field, an eggshell completely around it. But we can flop between orbit and shell. So I want you to think of every row, you call it an orbit or a shell. Let's start drawing our Bohr diagram. Hydrogen is element 1. And we put in 1 electron. How'd you like that animation? You have no idea what this took 20 years ago. Then we move to the second atom, helium. And there's the second electron. Now this orbit is full, so the usher comes in and he puts that rope around it and says, oh, the section's closed, nobody else goes in there. We now move to element 3, which is lithium, which needs 1 more electron. But notice, why does this just say number 1 here? Lithium has the first 2 electrons plus another one in the new shell, so it looks exactly like hydrogen from the outside. It has a single electron on the outer wall. Then beryllium comes in, and we have 2 on the outer wall, for a total of 4. 3 on the outer wall, for a total of 5. 4 on the outer wall, for a total of 6. Isn't that cool? This is like days of work it took me to do this. Now the second row is complete. The second shell is complete. It gets roped off. We move 1 more. Sodium has 1 electron in its valence shell, but it has a total of 2, 8, and 1. It has a total of 11. But what we're seeing is the first column of the table is characterized by elements that only have a single electron in their outermost shell. Then magnesium looks remarkably like beryllium from the outside. But from the outside of a castle, all you're going to see is that outer wall. You won't see the fact that magnesium is different than beryllium. If you attack castle magnesium and go, hey, castle magnesium is just like castle beryllium, only 2 guys on the outer wall. But you attack magnesium and you get over the outer wall and go, crap, there's 2 more walls inside. You couldn't see them from the outside. Then we have aluminum, silicon, phosphorus, sulfur, and then the valence shell is closed and she's done. The textbook likes to say the noble elements here have a complete octet. That's what they want. I don't never like that because the first row, there is no octet for helium. It's only 2. So I call these full valence shells. Now, does this mean the next row, that orbit should have 18 positions? Yes and no. It has 8 and 10. So potassium is going to have 1, calcium is going to have 2, 3, 4, 5, 6, 7, 8. jumping over these guys who have no pattern. So you will never be asked to draw the Lewis dot diagram of these guys in grade 9. I'll just show you how to get the answer. But you can bet your bottom dollar it's 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, all the way down. And these are almost always 3 to 8, all the way down here, with exceptions. You are not going to be asked to ever draw one of these past scandium. Okay? So now you see how the Bohr diagram and the Lewis dot diagram, every element has a unique Bohr diagram, but its Lewis dot is shared with many others. And the fact is that if they have identical valence shells, they will have nearly identical chemistry. So sodium chloride tastes salty, and that's where sodium is. Potassium chloride will taste salty too.